In this video, I'm going to go over some of the basic exponent laws that are covered in the grade 9 Math Alberta curriculum. There is also a download to this sheet here so you can follow along while I'm going through all the examples. Okay, so the first thing that we need to be aware of is what actually makes up the exponent. So the exponent is made up of the big number here, which is called the base. Then it has the small little number, which is this here. That is called the exponent, or you'll hear it interchangeably called the power. What the exponent does is it tells you how many times the base is multiplied by itself. So it is very tempting to see these numbers here and go 5 times 3 is 15. That's not the case with this example at all. What we're actually saying is we want to think about this 3 here as like a screenshot. So we're taking that 3 and we're copying the 5, the base, 3 times. So really what we're doing is we're going 5 times 5 times 5. So it is not 15, but rather 125. Okay, the other thing that we need to be clear of is the type of ways that exponents can be represented. So one of the ways, of course, is the one that I just showed you, which is the exponential form. So that's just the base, that big number, with the exponent or the power. So I'm going to go 3 to the power of 6 this time. Then there is the expanded form. So this is the base that is fully written out and copied the amount of times. So in this case, that would be 3 times 3 times 3, and you got it. We're going to keep doing that until we get to 6. Then the last one is the standard form. So the standard form is basically the answer to that exponent or to the expanded form. So that's going to be 3 times 3 times 3 times 3 times 3 times 3. So in this case, it is 729. Okay, so the first law when it comes to exponent laws, and one of the things I want to be clear here is the laws can technically be represented in any order. I just put it in this order here because it makes the most sense to me and hopefully it makes the most sense to you. So if we're looking at what I call law 1, that would be the powers of 10. So basically what we're doing is we're taking the number 10, which is the base, and we're multiplying it by the exponent, right? So remember that exponent is going to copy that number that many times and tell us what it's going to equal. Sorry, so that means it's the number of times indicated by the exponent. Now what we can do is we can actually look at those numbers and figure out what it's going to be. So for our first one, we're saying 10 to the power of 1. Well, that means we've just screenshot, or we just have one copy of the 10. So that is just going to be 10 on its own. Then the second one, you guessed it, is to the power of 2. That means we're going 10 times 10. And I'm just going to go ahead and add the standard form, which means we're looking at 10 times 10, which is 100. Okay, the third one, you're getting the idea, is going to be the same thing, but it's 10 times 10 times 10, which is not equal to 100, but it's 100 times 10. So that is going to be 1,000. We're just adding that 0 on there. Then the last one I have, you can see, is to the power of 4. And that's going to be 10,000. Now, one of the things that we can use, and we're not going to focus on it too much here, it's more important in, at least in Alberta for grade 10 science, is scientific notation. So basically that's just a way that we use to write very, very small numbers or very, very large numbers. So just something to kind of keep in the back of your mind is going to be scientific notation. Okay, so an example of scientific notation, again, not something that you need to worry about, but something to keep in the back of your mind, would be like this example here. We've got our large number here. We've got 7 zeros, and then before the 7 zeros, we've got 2 digits here and our starting number of 4. So with scientific notation, what we're doing is we're moving the decimal spot that's at the end. So if you remember, every whole number has like an invisible decimal spot at the end of the number. We're moving it to the left in this case. So we're taking that decimal spot, moving it to the left until it becomes 4.5. So the amount of times it takes to get to 4.5 is 9. And so when we write it out as scientific notation, it's 4.5 times 10 to the power of 9, okay? We can also go the other way. So if we move that decimal point to the left, and sorry, my laser pointer is really big here because I'm super zoomed in, then we know we're moving it 7 spots to the left, so it's going to be indicated by -7. Again, if you are in grade 9, this is not something you need to worry about, but just something that, again, you could be aware about for next year. Okay, so we are looking at Law 2, or what I'm calling Law 2, which is multiplying powers. So the first thing that I really want to be clear is the only way that this is going to work is if the bases, that big number, if the bases are the same. If they're not the same, then this whole thing doesn't work, okay? So what we're going to do if we are multiplying powers and the bases are the same, we're going to keep the base and just add the exponents. So with this example here, what we're saying is the base is x, right? We're going x to the power of m times x to the power of n. So the bases are the same, and then the exponents are going to be different. So this would be x. We're going to keep the base. We're going to add the exponent. So in this case, we're going to add m plus n. Okay, that might be really, really tricky. So let's try it with some actual number examples. So with this example, I'm going to go 3 to the power of 2, and we're going to multiply it by 3 to the power of 3. So again, we can go ahead and just add those exponents. So we're going to keep the base, which is 3, and we're going to add the exponents. Well, 3 plus 2, or 2 plus 3, I guess in this order, is going to be 5. So that is our answer. Now, let me show you why that works, okay? Now, you don't always have to prove it in this, but it's important to understand why it's working here. So what's happening is 3 to the power of 2 in expanded form is 3 times 3. That one's good. And then of course, with our other one, 3 to the power of 3, that's 3 times 3 times 3. Now remember, we're multiplying all of that. So I'm going to bring down this multiplication symbol here. Okay, so what's happening here? We've got a base that's consistent. It's going to be 3, and it's being repeated 5 times. So when I expand all of this out, what I'm actually going to get either way is 3 to the power of 5. So that is how we multiply exponents with the same base. Okay, let's try a different example. So I have here -5 to the exponent of 4, and we are going to go ahead and multiply that by -5 to the exponent of 3. Now, don't let that negative trick you. The base is still the same, right? The base for both of them is going to be -5. So that means we can just go ahead and do the same thing, and we can add those exponents. So that's going to equal -5. We're going to keep that base to be the same, add those exponents, and that's going to give us 7. And if you wanted to, you could give the expanded form. It's not asking for it here, but I'll tell you what it is anyway. 78,125. Dividing exponents. So the law with dividing exponents is kind of the same as multiplying, with one exception. So when we are dividing powers, again, we need the bases to be the same. We're going to keep the base, and in this case, we're just going to subtract the exponents. Right? The example that I kind of want to show you is right here, where we can see we've got x to the power of m divided by x to the power of n. So I've written it in both a fraction form and our classic division. So remember that fraction bar can always be considered as a division bar. So in this case, we're saying the two bases, and they've got their exponents, those are being divided by each other. So now we can go ahead and say that's going to give us x to the power of m minus n. So again, let's look at that with some numbers here. So I have 5 to the power of 5, and I'm dividing that by 5 to the power of 3. So again, the bases, that 5 is going to be the same here. And what we're going to do is we're going to divide them. So that means we're going to subtract them, which is going to leave me with 5 to the power of 2. So let's look at, again, why this works here. So if I were to expand these, I'm actually just going to move our answer down here. If I were to expand these, the top portion, the numerator, is going to be 5 times 5. So 5 to the power of 5. And then the bottom is going to be 5 times 5 times 5. So what happens here is you are basically dividing a number by itself for a certain amount of times. So when you take a number and you divide it by itself, you get a 1. math people, we don't always write the 1. So then, well, let me show you what it looks like. If we cross it all off, this 5 is going to be divided by that 5. So that's going to leave us with 1. This one by this one by this one. So we don't need to worry about those ones. They're going to be our invisible ones. We don't actually end up writing it. But our final answer leaves us with 5 times 5. So that's going to be 5 to the power of 2, which is what we notice the same answer I got here. So that's why it works. But again, we're using our divided power law, so we can just subtract the exponents. Okay, let me show you another example with negative exponents. I'm just going to erase this so I've got some room. So same idea as last time. We have negative 2 to the power of 8, and we're dividing that by negative 2 to the power of 3. So again, we're going to go ahead and subtract those exponents because the bases are the same. That's going to leave me with negative 2, and I'm going to put some brackets around those. And those brackets are just to give that negative a hug, saying that that whole base is negative 2, okay? Sorry, I didn't explain that in the previous one. We're then going to go 8 minus 3. Well, that's going to give us 5, and that is our final answer. If I wanted to write it in standard form, that would be negative 32. Okay, law number 4 here, if you will. So with this one, it does get confusing with the multiplying exponent laws, but what's happening here is this is the power of a power, okay? So that means you have your one exponent already there, but you also have a power on the outside of it. So what that looks like for the actual calculation that needs to be done is it kind of goes back to that distribution that you may have learned in grade 8, where we're going to just multiply what's outside that bracket to what's inside the bracket. So that's going to leave us with x to the power of m times n, or n times n, it's not going to matter. So let me just actually show you what that looks like with an example. So in this example here, I have 4 to the power of 2, and we're raising that whole thing to the exponent of 3. So again, that 3 is going to get multiplied inside here. So that's going to leave us with, well, let me show you why that works. That's going to leave us with 4 to the power of 2 to the exponent of 3, which means this gets repeated 3 times. And then we can think about, because it's exponent squared, well, that means each 4 inside those brackets is also 2 of them. Again, that looks like this. So this one here is going to be 4 times 4. This one here is also 4 times 4. And then this one here is 4 times 4. So all together, we've got 1, 2, 3, 4, 5, 6 4s that are all being multiplied by each other. So by doing that shortcut, you're getting the same thing here. Altogether, that's going to leave us with a standard form of 4096. Okay, I've got law number 5 here, or what's called the product law. So with this one, what we have is we've got 2 or more things inside the brackets, and then there's an exponent on the outside of it. So what we're going to do for this one is we're going to take the exponent and apply it to everything inside that bracket. So that means our x is going to have a power of m. Oh, this is a typo. That should be to the power of m. That should be to the power of n. And then this should be also to the power of n. So what this looks like with numbers is, let's say I've got 3 times 2, and we've got it all raised to the power of 3. So that 3 is going to get applied to everything inside that bracket there. That means we have 3 to the power of 3 times 2 to the power of 3. We can go ahead and evaluate those. That's going to give us 27, because remember that one is saying 3 times 3 times 3. And then our next one is 2 to the power of 3, which will give us 8. Multiply those together, that's going to give me 216. Okay, the next law I've got here is called our quotient law. So with this law, it's the same idea, but what we're going to do is apply it to both parts of the quotient. I'm going to write in the word here, both. So with this, again, just like last time, everything inside the brackets will have that exponent. So it's almost like as if I'm just distributing it to everything. So in this one, we've got x to the power of n, as we can see right here. and y to the power of n. And then of course, if the bases were the same, you would go ahead and evaluate it, but that's not the case with this one, right? We can see the bases are different. So as an example here, I'm gonna say we've got 2 to the power, or excuse me, 2 over 9, and everything is raised to the power of 2. So again, that means everything is really going to get, everything inside that bracket is going to get squared. So that's going to leave us with 2 to the power of 2 and 9 to the power of 2. We can then go ahead and evaluate both top and the bottom. So that's going to give us 4 for the top and 81 for the bottom, and that's going to be our answer for that one. Okay, here is our last law, law number 7, as I'm going to call it here. So this one is one of the most simplest laws ever. Any base that has a power of 0 will always equal 1. So for example, let's say I have 7 to the power of 0, well, that's going to equal 1. I'll go ahead and explain why that is if I have something like this, 5 to the power of 3, and we're going to say it's also under 5 to the power of 3. We know in something like this, the bases are the same, so we can subtract the exponents. So that's going to give us 5 to the power of 0, right? So why does that equal 1? Well, let's expand everything for the top. That's going to be 5 times 5 times 5 over the same thing on the bottom. Well, remember what I said earlier, the same number on top and the same number on the bottom. So we're going 5 divided by 5. Well, all of that gets canceled out, if you will, or really it turns into 1. So that means we really have 1 over 1, which equals 1. So anything to the power of 0 is 1. If that didn't make sense in the QR code there, I also have a link to another video explanation. It's not me, but the explanation is really good. Okay, so I hope that helped. In the description down below, I have lots of worksheet for you to practice everything. Keep in mind that all the examples I went through are very simple, basic examples. You'll see that our questions can start to get a little bit more complicated and apply a multiple of these laws. But until then, I'll see you all in the next one. Have a great time learning about exponents, everyone.